of the tissue. So when we're doing the endoscopy, so most of the time we through the endoscopy monocular camera, we see something like this, which is basically the surface of RGB, or sometimes we have narrowband imaging, but we are not able to see the thing underneath the tissue. If we want to see the thing underneath the tissue, we either want to have the ultrasound, for example, endoscopic ultrasound to see what the layer structure, because a lot of diseases are happening underneath the tissue. So that layer structure, mucosal layer, submucosal layer, muscular layer, really indicate the stage of the lesion. It could be stage 0 all the way to stage 4, something like that. So we're not able to see that through RGB monocular endoscopy. So we have to have new diagnosis or whatever approach to see through the tissue. The current standard is to do, for example, the biopsy, the tissue biopsy. We have a grasp going into the lumen and the luminal wall, and we grasp the piece of tissue and we send it to the lab pathology. And they're going to do the H&E histology. They can have the structure like this, but that will not be accomplished in real time on site. So we developed the endoscopic optical coherent tomography, actuated by magnetic field. So the way we actuate it, it's sort of we control both the position and orientation so that we can navigate again from point A to point B, for example, from the oral opening all the way to the esophagus or the stomach or even deeper location. While we're there, we also, because it's sort of like LiDAR, so on top of the car, they're doing the high-speed rotation. So here, we also want the optical coherent tomography probe to have high-speed rotation so that we can have high-quality imaging like this. So for the first time, we introduced the magnetic actuated OCT probe so that we can do the programmable imaging in a compact curve and localized area. So this is the 3D reconstructed scenario, and this is for example, we do the pull by the magnetic actuation, while we can, after the layer cross-sectional imaging, we can reconstruct, and we can actually see the very nice correlation between the histology layer and the OCT layer. So by doing this, meaning that potentially in the future, we can have real-time optical biopsy, can help a surgeon to quickly identify what is the disease stage, stage 0, 1, 2, 3, 4, which is otherwise not possible from the purely RGB endoscopy. So this is the magnetic actuation. It's actually quite straightforward. We have external magnetic field, internal magnetic, permanent magnet coupled with the reflector, the mirror, which should connect to the green lines, it's pathing or controlling the optical pathway. So the challenge is how to, for example, to have stable, continuous, smooth rotation. Well, we have this curve linear, and going through the very, very tortuous pathway in the lumen. Then we can also control the programmable pattern. So the scanning pattern is sort of like, if you look at the picture, sort of like 3D printing. It's exactly like that, but we are doing the scanning because sometimes the lesion open, only happening around one side of the lumen. We don't want to do the circumferential scanning. Instead, we want to have the reciprocal scanning, scan back and forward, and then we need to program the pattern. In the same way, we can do the intervention as well. After we have the imaging, we can do the real-time programmable scanning pattern and intervention pattern. So this is the imaging quality. So you can see on the right, so we try the technology on different anatomical environment. This is the phantom lung tissue. But that's not perfect yet. We still have challenges because the rotating speed with the magnetic coupling between the internal permanent magnet and external permanent magnet, sometimes we may lose step, especially we have a long actuation distance. So then a team has sitting right over here, so developed this pneumatic OCT. So it's very much like our soft pneumatic actuator, as I mentioned at the beginning. We're still doing tailored way to actuate the continuum OCT probe. And in order to overcome the tortuosity, because we need to, for example, for bronchi tree, we have a lot of branches like the tree branches. And we need to go through and overcome the tortuosity, the sharp turn. And while we're there, we need to have the high-speed rotation to give us distortion-free endoscopy, endomicroscopy, or the tomography here. So what we see here. So this is the challenges. And later on, we show a demonstration. We can see by using pneumatic optical coherent tomography, we can have really much better imaging quality if you compare the magnetic one. So we can control the rotation speed from, it's controllable, adjustable, fully programmable from 50 run per second all the way to a few hundred run per second. And the imaging quality is much better than the magnetic one. Again, we can see very good correlation between the histology tissue and also the tomography layer. This is the soft pneumatic catheter. As you can see here, we can control the bending left or right, up or down, and so that we can choose which bronchi tree, which generation of bronchi tree to go. For example, this is the left superior lobe or lower superior left lobe. So whichever way is to, because we can do the 2D endoscopy to 3D pre-op CT registration, and then we do the navigation first, which is like driving the car from point A to point B. Once we are there, we have the OCT scan. Right? So we do the high-speed scanning, and then we can see the internal cross-sectional structure. So, and that is highly correlated with the pathology. So presumably that can be utilized in the future if this can be put into practical utilization, then we can have real-time corresponding between the OCT and also the histology. So similarly, we can push the optical coherent tomography into other nanoring, and then we do the we so-called neural OCTs, meaning that we do robotic optical coherent tomography, push them all the way into the deep brain. And then we can have really nice, for example, high resolution imaging right over here, which give us a few micron resolution, which is not possible from MRI, magnetic resonance imaging, or CT is not possible at all. So this meaning that when we want to have really high resolution target imaging, especially deep in the brain, sometimes we want to do deep brain stimulation. We want to know where the target is. I want to really interact the tissue at really fine resolution level. So this can potentially help us to build up the closed loop neural intervention. So in this case, we're trying to do the imaging first. In the future, we can incorporate imaging modality with the deep brain stimulator. And the whole system is MRI compatible as well. So this is the actuation part. This is cable driven. We can also do hydraulic driven. This is we can have different option to enable the OCT steering. And this is a setup. You can see this is the small animal, and this is the optical system, optic module. This is the mechanical or robotic module. And so this is the robotic setup. So because when we are doing the, for example, tool-teaching interaction, especially for neural application, the tool-teaching interaction force is really critical to avoid potential excessive force or damage to the delicate tissue. So in this case, for example, we have the Fukushima suction tube or suction instrument, and we developed the multi-dimensional, in this case, three-dimensional, one-dimensional force, two-dimensional torque, which is disposable, printable. It can be easily mounted on top of the suction tube. We can detect the micronewton level force so that they can alert just in case some excessive suction force between the instrument and the tissue. So we can imagine if, for example, apply, just like vacuum, we do cleaning for the room. If you apply excessive vacuum force or pressure, we can damage the ring. So that's something we want to avoid. And we can also apply a similar approach, further again the dimension and the resolution we apply to the catheter intervention. This is the cardiac ablation catheter. We can also attach the fourth and top sensor at the distal tape. We can detect the micronewton level force. So micronewton level force is pretty much really gentle. It's not even detectable by our human, for example, skin or finger. Okay, lastly, I guess.
No, it's not.
Yeah, my
time. You have a long time.
Yeah, so this is the last part. So we already show sort of between tethered and tetherless configuration for the origami continuum on tissue, how to adjust and modulate the interface to make sure they are complying and applicable in the human luminal environment. So recently we developed a new material and also the activation approach we call regraftable ferromagnetic soft continuum. Because we have certain scenario, we want the continuum structure to be, first of all, to be really small, sub-millimeter level in terms of the outer diameter. Second of all, we want it to be reconfigurable inside the human body. So meaning that once we, for example, we do the endoscopy or the instrument, the continuum structure or catheter or gateway going through the working channel, once they are inside the human body, we still want it to be reconfigurable. We make it, for example, to be splittable, or we can divide it on-site rather than taking out and then dividing, or we can merge it inside on-site. So we'll show some of the examples. So we show that to, again, the same slide to compare. This is not in terms of metamorphic, we are not able to divide them or not able to, for example, merge them once we are we deploy whichever one of these systems inside the human body. We're not able to do too much change. Well, of course, the kinematics can be based on the pre-designed kinematic, we can control that, but we are not able to merge or divide. And then we think about the, for example, the phase transition material. We already have a lot of phase transition material which can do phase transition from really soft, like kilopascal, to really hard, but without intermediate stiffness level. So, for example, megapascal, from kilopascal to megapascal stiffness, that's the majority of the stiffness level for our soft luminal tissue. So this is the part missing for the current phase transition material from liquid to solid. So it's either too soft, like water or fluid, or too hard, like hot piece metal gigapascal, but not something in between available. So we want to develop this reversible elastomer fluid phase changing material for continuum catheter. application. So this is the way to do the fabrication involve the thermoplastic material, metal fluid, malleable material, and elastomer and magnetic nanoparticle. To putting them together, and then we can have this phase transition capability. It could be a lot of different geometry. It could be, for example, like a planar structure like this. They are blocked by the really narrow gap, right? So almost no space for the solid shape to go through. And then we do the phase transition, convert it to the liquid, spreadable, flowable shape, and they can squeeze themselves going across the really narrow gap. After going through the narrow gap, they can still maintain the magnetic responsiveness moving further. So we can see actually we can pre-program the gap to change the shape actually. You can make one piece, two piece, three piece on different structure. It's like injecting, right? So there are a lot of other potential as well. So because we have this phase transition capability, it's pretty much self-healing or self-healable. So for example, we have the structure like this. We can literally cut it into two pieces. And then even though we keep a little bit distance, and then we can still do the self-healing, controllable healing. For example, we do the phase transition a little bit, and then we actuate. So if you look at the interface, right, edge-to-edge interface, we can control them to move towards each other, and then we do the self-healing. So everything is done untethered, in an untethered way. Of course, we can have different way to do the self-healing. We can cut along the longitudinal direction, and we can cut into two pieces, and then we can see the self-healing capability. Then the question is, so we demonstrate this thing, what is the application? How can we utilize the technology here inside the human body? So there are a couple of ways we explore. So one way, for example, we can reconfigure the existing rigid kinematic structure. So for example, we have microneedle array. If we look a little bit further later on, right? So there's a microneedle here hidden at the beginning. We can, because when we imagine this is a capsule endoscopy, we can swallow the whole thing, can put it into the capsule and swallow, and then the shell dissolved. We expose the whole thing, but we don't want to expose the microneedle. Because the needle is sharp and can be damaged, can damage the luminal wall. So we do the actuation navigation first. Once we the location, we can melt down the structural interface, and then we can expose the needle. Similarly, so this is one structure at the beginning. Once we deploy the whole thing inside the human body, we can melt down the structure and reconfigure the constraint of the kinematic, and then we can see they have much bigger range of motion. They can even be fully foldable. But otherwise, at the beginning, it's not fully foldable. So there are many ways, because we can control the origami interface to constrain the structure, and then we can, for example, melt down the constraint, and then they can be reconfigurable. We can change the kinematic configuration on site. So that's the origami graftable material, the reconfiguration. So what about the continuum and the really tiny, soft sub-millimeter actuator, catheter, or gangway? So there's a experiment did in, for example, foreign body retrieval. So we just do the regular way to do the endoscopy. Once we are there, we form, for example, to grasp the foreign body. And we can do the self-merging at the distal tip. In this case, they reconfigure as a basket. so that they can have full closure, right? So in that case, they can engage the foreign body really, really well, just meaning really strong grasping capability because they fully enclose the foreign body. But otherwise, if you don't have this reconfiguration, then we may have slippery slippery actuation, may not be able to retrieve the foreign body.